So, welcome to the next video. So, let me give you a recap. Why we started everything. So, we saw initially that to increase the CPU efficiency was our main target, okay? And to increase the CPU efficiency, we had to go for the multitasking and preemptive environment operating systems, alright? So when we went for the preemptive operating systems, we could see that there are critical sections, okay? And because of these critical sections, we ended up in inconsistent system. Then synchronization mechanism came to rescue us from this problem, okay? So after synchronization mechanism, we have high CPU efficiency because we are in a preemptive operating system, okay? And we have solved this inconsistency using the synchronization mechanism. So as a result, we have achieved some CPU high efficiency, okay? So now you know what synchronization mechanism is, okay, and what is the main purpose of this synchronization mechanism, okay. So synchronization mechanism is nothing but set of instruction, that is the code you are writing. So when you are saying you are writing a code, then the next question is which algorithm you are following, all right. So there will be multiple algorithms for a synchronization mechanism, okay. So your friend may come up with one synchronization algorithm, you may come up with one synchronization algorithm, I may come up with some other synchronization algorithm, okay. But which one is correct and which one is wrong? How to judge that? Let me show you how will you be judging which synchronization mechanism is correct and which one is not correct. So when a synchronization mechanism is accepted, okay, this is a condition for a successful synchronization mechanism. These are the conditions. So in order to be a successful synchronization mechanism, that algorithm has to match these conditions. So when a synchronization mechanism is accepted as correct mechanism algorithm, all right. So there are two type of conditions. One is primary conditions. There is no escape, that synchronous mechanism will have to match these primary conditions, and sometime a synchronization mechanism may or may not match the secondary conditions. Alright. So what is the moral? The moral is if your algorithm or my algorithm does not match one of the primary conditions, then we will be discarding that algorithm immediately. Okay. And if a synchronization mechanism does not match one of the secondary conditions, we are still fine with this. There is no bound that we will have to match all of the secondary conditions. But in case of secondary condition, okay, if we are coming up with any synchronization algorithm, our aim should be matching as much as possible of these secondary conditions. Now let me show you what are the primary conditions and what are the secondary conditions. So the first point in primary condition is mutual exclusion. So I have already told you what mutual exclusion is. So once process P1 is into the critical section, P2 should not be accessing the critical section. Alright, this is a mutual exclusion. So it says once a process is accessing the shared resource, no other process should jump into and access the same resource. Okay. So once P1, let's say there is a count variable, once P1 is accessing this count variable, okay, P2 should not be jumping into in accessing the count variable. If P2 started first, then P2 will have to wait. Once P1 is done with accessing the count variable, then only P2 comes and does this minus minus operation on count variable. And similarly vice versa. If P2 comes first, then P1 will have to wait for P2 to be finished. Then only P1 can jump into and access the count variable to make the count plus plus. Okay. So if you see the dressing room, if you remember the dressing room example, okay, let me add one page. So okay, if I give you the dressing room example, let's say this is a dressing room, okay, this is a curtain, there is no lock and no gate. Let's say there is a tag. So person one, let's say person one came early and person one got the access on the dressing room, and now P2 came and P2 saw that, oh, this is occupied. Okay, now P2 cannot jump into this dressing room. Now P2 will have to wait till P1 is coming out of the dressing room. Alright. Similarly, vice versa, if let's say P2 came early and then P1 came and P1 saw this is occupied, okay, P1 directly cannot jump into the dressing room. P1 will have to wait till P2 is done with using the dressing room. Once P2 comes out, then only P1 will be able to get into the dressing room, something like this. So this is the mutual exclusion. So it says at a time only one process will be accessing the dressing room, and in this case only one person will be accessing the dressing room. In context of operating system, at a time only one process will be accessing the shared variable. Okay, fine. So second, okay, fine. So this is the first primary condition, that it has to satisfy mutual exclusion. So the second primary condition is progress. So what is progress? So let's say there is a process P1 and there, okay, let me write it down. Let's say there is a process P1, there is a process P2, and there is a count variable. Okay, fine. So what progress says is, let's say P1 does not want to execute count plus plus. Okay, that means P1 somehow for any reason P1 does not want to access this count variable. Okay, then P1 should not be stopping P2 from accessing the count variable. All right. If what I said, let me repeat. If P1 does not want to access the count variable, then P1 should not stop P2 from accessing the count variable. Similarly, vice versa. If P2 does not want to access the count variable, then P2 should not be stopping P1 in accessing the count variable. Alright. If I get into the dressing room example, let's say there is a dressing room, okay, there is a curtain and there is a tag, okay, there is no gate, no lock. Let's say person 1 and person 2 is there, okay. Let's say person 1 is still selecting the dresses that he wants to try, alright, and P2 is done with selecting the dresses that P2 wants to try. So it should not happen that, so as of now, the dressing room is empty. P1 is still choosing the dresses. So now this P1 should not be stopping P2 from accessing the dressing room. And vice versa. Let's say P2, now P2 is still choosing the dresses that he will be wearing. Alright? And P1 is already done with choosing the dress and P1 wants to get into the trial room or dressing room. So now, given that P2 is not ready to get into the dressing room, P2 should not be stopping P1 from accessing the dressing room. Alright, so this is what progress says. Okay, so progress and mutual exclusion, these two are the primary conditions. So what do you mean when I say primary condition? What I really mean is, if tomorrow you come up with your own synchronization mechanism, your synchronization mechanism has to match these two conditions. One is mutual exclusion and another one is this progress. Alright. So now let me get into the secondary conditions. So secondary conditions, let's say you are coming up with an synchronization algorithm which is satisfying the primary conditions and which is not satisfying the secondary conditions. Then also your algorithm will be considered as synchronization algorithm. But your target should be maximizing in matching the secondary conditions as well. Okay. So what is the first secondary condition? So that is bounded waiting. I will explain. And what is the second? That is no hardware dependency. So what bounded waiting says? Let's say there is a process P1 and there is a process P2 and there is a count variable. Okay. So let's say P1 and P2 both are trying to accessing this count variable. Okay. P1 is trying to do count plus plus. Okay. And P2 is trying to do this count minus minus. P1 and P2 both wants to get into the critical section. Okay. Now it should not be the case that every time only process P1 is getting executed and process P2 is never getting the chance. Okay. So if this is the case, that P2 does not even know when P2 will get a chance in accessing the count variable. So it says we are not matching the bounded waiting. So there is no bound in waiting. Alright. It may happen that P1 says, hey P2, you please wait. I have the highest priority or some other reason. For the next 1 year, I will continue executing this count plus plus, and after a year you will get a chance of doing this count minus minus. Okay. If that is the case, then there is a bound in waiting. P2 will have to wait for max 1 year. But if P2 does not even know when P2 will get a chance, okay, then we show there is no bounded waiting. Alright. So there should be a time bound. By that time, a process should get access on critical section or shared resource. Okay. It should not happen that a process is waiting infinitely for getting into critical section or to access the shared resource. It should not be happening. Okay. In that case, we will be saying there is no bounded waiting. So the last thing, there is no hardware dependency. So let's say you have come up with an synchronization algorithm, but that works on your laptop only. It does not work on my laptop. So do you think this is a really good synchronization algorithm? Answer is no. So your synchronization algorithm should not be expecting anything from operating system. Alright, it should not be depending on the hardware on which the program is running on. Alright, before getting into more deep, let me clear one more terminology, maybe two more terminologies. Okay, so one is user mode, another one is kernel mode. So what user mode is? I will come to the user mode slightly later. Let me cover the kernel mode first. Let's say this is the operating system, the entire operating system, okay, responsible for multiple things. So there will be a core part of your operating system, okay, which enables your operating system to work properly. So this core part is called the kernel, okay, and this kernel enables operating system to work as expected, okay. So you can say Kernel is the core part of the operating system. Kernel helps the operating system to work. Okay, kernel enables operating system to work. So in kernel mode, the processes are non-preemptive. What do I mean by that? If a process is executing some lines from this kernel mode, okay, that process cannot get preempted. Once the process is done with executing these codes related to the kernel mode, then only that process gets the permission to get preempted, not before that. Okay. So now let me explain one more mode. So that is user mode. So what user mode is? Whatever program you are writing, that is a user mode program. So program in restricted environment, okay? You are writing printf hello world or scanf, some integer value you are trying to scan, all right? Or maybe you are doing something else, okay? So whatever you are doing, whatever coming from user end or programmer's end, that is user mode program, okay? User mode instruction. So whatever manually you are writing in your using your keyboard, you are writing codes, you are writing instructions, those are in user mode, all right? So this is in restricted environment. Why restricted environment? So it cannot access the hardware directly. None of the hardware resources your program can directly access. So if you are writing something and you are expecting some output at the hardware level, so you will have to go through by the kernel. Okay, you will have to talk to kernel, and on your behalf, your kernel will talk to the hardware. Okay, let's say you are writing printf hello world. Okay, let's say printf hello world. Okay, what will happen, let's say there is a process p1, so you are expecting this hello world to be printed on your monitor. Okay, so your program cannot directly do this. So what will be done, your program will talk to the kernel and will say, hey kernel, I want to print hello on the monitor. And for the rest of the part, kernel will take place. Okay. And for the rest of the part, kernel will be responsible to print that hello on the monitor. Alright. So if you see the flow looks like this. User mode program. So whatever you have written executes a system call. What is system call? So system call is something, okay? System call is something that helps us in talking to the kernel. Whenever we are requiring any OS services, it might be on some hardware or it might be in some memory. All right. So using system call, we talk to the kernel. All right. So user mode program executes a system call. Okay, this is how the flow is. User mode program executes a system call. So now CPU switches to kernel mode. So once CPU sees, oh, there is a system call is taking place, then your CPU is switching into the kernel mode. So after that, this OS, to be very precise, is kernel. Okay. Now this operating system performs that task on behalf of you. Let's say you have written printf hello world. How this flow will look like? Let's say printf hello world. Let's say hello. Okay. So when this is at user mode, okay. So so when this printf is executed, actually this is calling some system calls. Okay. This system call is using the system call. Our program is talking to the kernel. Hey kernel, I want this hello to be printed on the monitor. You please help us. Now the mode is changed into kernel mode. Okay, this mode is changed into kernel mode, and your kernel, now your kernel comes into the picture, and your kernel does all the needful jobs that it has to do so that you can see hello on your monitor. Okay, that is how the flow is. So I have already explained, kernel is the core of operating system. All right, then access on all memory and all other hardware instruments. All right, this is fine.